Okay. Let's talk about the manufacturing lab, the Wharton composite manufacturing lab. And there's also a sign-up sheet going around. It already has all of your names on it. And I essentially don't want to do, you want to start putting a check mark in front of your name on lab 4, right? Lab 4. Just put a check mark. Don't need to write your name, just put a check mark. The names are here. Just find your name. Did you find your name? Yes. Just find your name, put a check mark in front of your name under lab 4. Yeah, so in this lab, we are going to study the flow through porous media, essentially just a glass fiber fabric, and we are going to measure the permeability of the resin we are using, the effective permeability of the resin passing through a glass fiber. And then eventually we're going to perform a statistical analysis of the permeability. Your assignment here is to capture a video of the resin moving through the fiber, and we're going to talk about all of this, analyze the data, and calculate the effective permeability, and all of the essentially everything that comes with it. This lecture, we're going to talk about composites, we're going to talk about applications of composites, we're going to talk about manufacturing of composites, and we're going to talk about flow through porous media. One question though, who has already passed the composites course? Or who is already in the it is not a mandatory course for you? No? That's all right. So whatever theory you need to know, we're going to talk about here, and most of these lectures are essentially focused on the applications of composites and what those are. I'm sure you know what composites are. Essentially, when you combine two different material to create a stronger material, in most cases, for most applications, we have built composites. And composites, we already have composites in nature, like wood is the, I guess, most famous composite material. And you have seen I'm sure you have seen the applications of carbon fibers around you a lot. They are gaining in popularity. Essentially what we have is, we have a fabric, we have some sort of fiber, we have a resin, combine them together, cure them to have a composite plate. And in this lab, you are going to actually build this composite plate using one of the techniques, composite manufacturing techniques. But why do we use a composite material? The thing is, with building a composite material, you can control the stiffness, the strength on all the material properties. You can change the material property, you can use the stronger material. As I mentioned, for example, as you can see here, we have the 3 different composites, specifically here, composite material, and you're going to see their modulus of elasticity in one direction is actually higher than steel. Young's modulus in some cases. This is something that you're going to see again and again and again with composites, that they are in a specific direction, they can be stronger than the strongest metals in the market. So hence the application, the use of composite, and they are always, in most cases, they are lighter than metal. So you have built a material that is stronger and lighter than metal. It will make it, again, it is essentially more feasible. It is better to use that material in most applications. That's not true in all directions though. Like composite strength is very directional. It really depends on how you have built your fiber, essentially. But this is another composite. Where do we use composite? If you take a look at a modern airplane, this is a modern, and here you can see a 787 airplane. All of the blue areas are carbon laminates. Essentially, most of the plane, so 50% of the plane nowadays is built from composites. It is not just planes though. You can see that BMW i3 is an electric car, one of the earliest electric car. I think it came out in 2014, and it is all the chassis of this car is made from composite. So the battery pack they have included in the car is actually like 20% of the battery pack in Tesla, but its range is essentially half of the Tesla, which tells you how important is the weight and the material you use in your build, as well as the aerodynamics of the cars, of course. And power generation, wind turbines. Wind turbines mostly are built from composite nowadays. A lot of other things, like in bioengineering, the biomedical engineering, a lot of equipments are built with composites. So composites are very important in general. Other examples of composites. Okay. So how can we build a composite plate? You have to select the fiber in most cases. I'll get the most famous one. The most common one is a carbon fiber. Well, the one we use in the lab is a glass fiber. Essentially, these white ones. You're going to build a composite plate using a glass fiber. You have to choose your fiber, and then you have to weave your fiber. There can be different patterns, right? And these different patterns are the thing that is going to determine the strength of your composite eventually, right? Like for example, this pattern, this woven pattern here, is not going to give you the strongest material, but its strength is not unidirectional. So it is strong in both directions, comparable to metals, but it's lighter than metal. So you have seen this woven pattern a lot, I'm sure, in all of the carbon fiber you have seen around. The reason we see this a lot is because the strength is essentially very similar in both directions. Okay. Make sure if you just came in, make sure you put a check mark in front of your name on the sign-up sheet. Okay. Yeah, we did talk about this a little bit. One problem we have had with the composite is that they're built from thermosets, and the problem with thermosets is that once they're shaped, they cannot be reshaped, so we cannot melt them. But we're moving away from thermosets. I mean, they have their own applications, but with the introduction of thermoplastics, wherever you need to melt and reshape a composite plate, you can, because thermoplastics are reshapeable. The differences between thermosets and the thermoplastics. And we're going to use thermosets in the lab. So we're going to use a thermoset resin to build our composite plate. These are liquid at room temperature. The thermosets, they need heat or a catalyst to cure. And when you cure it, you won't be able to liquefy and reshape your composite plate. And they have a very low viscosity at room temperature. Okay. What are the processes in which we can actually build thermoset composites? Let's go from here. There are three main processes that we're going to focus on. First is the wet hand layup, then the RTM process, which stands for resin transfer molding, and then VARTM process, which stands for vacuum assisted resin transfer molding. And in the lab, we are going to learn how to do this. Essentially, when you know how to do the vacuum-assisted resin transfer molding process, you will be able to do the other two on your own. Right? The other two are going to be a little easier to handle. Not very well, but you will be able to do them. How do we do the wet hand layup? So essentially, let's say in the lab, let's say you are in the lab, you have your mold, you have to cut your fibers. The fibers are fabric, essentially. You just have to cut them off, put them on top of each other. Each layer, you have to add some resin and make sure that resin has impregnated your fabric. Add the other resin and so on. So add the other layer of another layer of fabric and so on and so forth. Let's say you want to have 8 layers of fabric. You have to do this 8 times, and you just have to let it cure, right, in room temperature. The problem with the wet hand layup is that you have to be a very masterful Essentially, you have to know this very well. You have to be a very skillful person to be able to make a good composite plate, right? Because it depends a lot on how you use this roller, how you impregnate the fabric with your resin. So I guess to fix that dependence on the operator problem, they have come with the RTM process. And the RTM process, of course, you have to cut your fabric first. That's the first step always. Then you have a mold. Just put everything on your mold, and then you have to put another mold on top of it, a closure mold on top of it. You add the resin to the whole system, and you just let it cure. That's it. So cutting, stacking, compaction, impregnation by injection, curing, and demolding are all the whole processes. And this is something we actually do in McNair. If you have ever been to the McNair Research Center, they do the hand layout, they do the RTM process, they also do the Wharton process. So Wharton process is very similar to the RTM process. The difference is you suck air out from one location, and that is going to bring the resin in, right? This will work better with the impregnation. You won't see as many, you shouldn't see any air bubbles in your system. That's the perfect condition. But with vacuum curation, with this vacuum pump, you won't see as many compared to the RTM and the other process. The Wharton process you're going to do then in the lab is going to look like this. So we have a vacuum pump here, a function here that resin is one thing we need to have in the Wharton process that we don't really have before is a distribution. So you are creating, right? But if it's still the vacuum fiber, let any resin. Remove all of the area. What you're going to do in the lab is not going to be as clean as this, but it's exactly the same problem. And you have to make sure that you follow all the safety protocols. You have your goggles on, you have your mask on, and you have your gloves on, safety gloves. Nothing's going to happen, but you have to be careful always. Okay. This is another button. Yeah. So, as I mentioned, the resin impregnation process is very important, and this is one of the problems we always have to deal with. That's why we have introduced the Wharton process in general. To make sure that we have a completely filled fiber, we have to know the permeability of the resin and fiber, the whole thing together. We have to understand it. So we have to do a fluid dynamics analysis to find out the effective permeability of your resin in this specific fiber. And this is going to be your job in the lab. So how do we do this? We have to go back to the Darcy's law. I don't think you have seen that Darcy's law in your fluid mechanics course, but you have seen if they did cover chapter 8 for you, which was the flow inside the pipe, you have seen something similar to it. Essentially, the Darcy's law says that the flow rate in anything is related to the pressure drop, right? The pressure change in the system, dPdx, among other things. These other things here is going to be the permeability of the system, the viscosity of the fluid, and also the cross-sectional area of your fiber, in this case, fiber and the distribution medium. So, what is important for us here? Specifically, the pressure gradient is very important, viscosity of the fluid is very important, cross-sectional area is very important, and then you have to come up with a method that let us calculate the flow rate in this whole system. Using all of these, we can find the permeability of the fabric, and based on this, we can essentially know how much suction do we need to have and what should be the speed, the flow rate of the fluid passing through your resin to make sure that we have a uniform spread of the resin. We are not going to use the equation as it looks like right now. One thing you have to keep in mind is that the permeability is directional. Permeability, especially in a composite material, permeability of a composite material can be different in different directions. Do we understand what permeability means? Yes or no? Okay. It is. I mean, you can know what it is just based on the word, right? Okay. Let's simplify. This is not a good thing. Let's simplify this equation a little bit. The first thing we want to do is to define this new parameter called the flow front velocity. And we are also going to design our experiment in a way that enforces a one-dimensional flow. So we only deal with permeability in one dimension and one-dimensional flow. So you are going to have you're going to cut a very long fiber, and you're just going to see the flow front moving in the same location at all times, right? And in the lab, you have to record this, and you're going to have a tape measure just beside your CL. So you're going to know what is the location of your flow front, that resin front, at all times. Yeah. And based on that, you can find the velocity and whatnot. But we're going to talk about it. So, what are the assumptions we are making here? We are designing our experiments to imitate the one-dimensional flow as much as possible. The main assumption is it's a one-dimensional flow. And for this one-dimensional flow, we are going to define a flow front velocity. This flow front velocity is going to be your velocity, whatever your velocity is, divided by phi. What is phi? Is the porosity of this fiber and the distribution media. What does porosity mean? No idea? Is there anyone in class who can tell us what porosity means? So think about it this way. When you're stacking these fibers on top of each other, there is going to be some empty spaces filled with air or any fluid that you're passing through, right? The porosity of any material is the ratio in the volume, essentially, the volumetric ratio of your material versus that empty space, right? That will be the porosity of the fabric. So if your fabric is more porous, right, it can let more resin in, like with higher velocity, easier, right? Which means that your permeability has to be higher for more porous material, right? At the same time, since the fibers have to be the strands of fibers have to be away from each other to have a more porous material, you're going to have a weaker material, not as strong as you want it to be. So there is always a balance between the porosity and the strength of the material. They are not directly related, but because porosity comes into play when you are doing a fluid dynamics and a fluid mechanics analysis, but they can affect each other. Okay, so how does our equation change? The Darcy-Law equation. What is the flow rate? How do we calculate the flow rate? Is the cross-sectional area multiplied by the velocity. That's the first line here. It is equal to negative permeability multiplied by the cross-sectional area divided by the viscosity multiplied by the pressure gradient. Okay, so if we replace Q with A multiplied by U and then bring in our front velocity, which is can be calculated based on the location of your front at each time, we can rewrite this equation as you see on the board. And then for the front velocity, again, front velocity is a location at each time. So we can calculate the front velocity as the derivative of location with respect to time, dx dt in this specific case. Where is the front again? Wherever your resin is at that specific time. How can we calculate this? You just have to put your cell phone out, record it, right? And then you're going to have the location at, let's say, 5, 6, 10 different times. Okay. So, can we rewrite the equation to look like this? dx dt is equal to negative permeability divided by viscosity multiplied by the porosity multiplied by delta P delta X. So we moved away from the gradient of pressure with respect to time. This is the second assumption we are making here. We are assuming the changes in pressure are linear, which makes the derivative just a difference, equals to a difference, which will make the whole thing much easier. So we are going to be left with this equation. Negative K divided by mu phi multiplied by P2 minus P1. What are these P2 and P1? P2 is the P at the outlets, which is where you're sucking air out. And P1 is the P at the inlet, which is where you are pulling the resin in, right? Does this make sense? One question, what is the pressure at the inlet? This is where you are pulling the resin in. This is atmospheric pressure, right? So if you're using gauge pressure, it should be 0, right? It is that they're looking at different, here's the outlet. So this makes your equation dx divided by dt equals to k divided by mu phi multiplied by p in divided by x. So what should we put for P here? What is our pressure? You said P in is 0, right? This is true. P in is 0. The gauge pressure is 0, right? What about P2? What is P2? I have to change this sentence here. It is going to be negative 14.7 psi, right? That's absolute 0, right? So this P in, if you're looking at it from gauge pressure perspective, has to be 0, and the P2 cannot be 0, but from absolute pressure perspective, this P in is going to be 14.7 psi, or 1 atmosphere, or 1.1 10 to the power 5 pascals, right? So the point is we already have the pressure we want, right? What is the X? X is the difference between essentially the length between the inlet and the outlet that you're pulling the resin in and when you're sucking air out. That is going to be your length. In this equation, we essentially have everything. We know the location at each time. We know X. We know P of N. We know the viscosity of the resin, because we are going to tell you what the viscosity of the resin is. And we can calculate the porosity, which means that we can easily calculate the permeability. You just have to get rid of this derivative, which we can do using this integral. So you have to use this equation to find the permeability of the fluid. Again, what do we measure in the lab? You just have to do a recording, right? And then you have to have a ruler or tape measure, whatever, beside your medium. So you know what is the location of your front, this X, at each time, right? Based on this, you can have a curve like this. See, location at each time, location at each time, location at each time. Which means that you're going to have more than one data point, more than a couple data points. Let's say you have 10 data points. You can extract as many data points as you want, because you have recorded the video yourself, right? You're going to have a ruler beside it. Which means that you can calculate more than one effective permeability, which will let you do the statistical analysis on this. Any questions? There are a couple of things you need to have before doing the final calculations. All of the equations you need for the effective porosity, the thickness and everything is listed here. You have to keep in mind that you are calculating the effective permeability for the distribution media and the fibers, right? There's a distribution media on top of the fibers. Whatever you need is the equations are here, and also the characteristics of the fiber and the distribution media are listed here. In the lab, depending on the number of groups you have in the lab session, there will be different number of layers. So if, let's say you have 3 groups, we're going to build a composite plate with 4 layers of fiber, 6 layers of fiber, and 8 layers of fiber. So they're going to have 3 different plates made. And if you have only 2 groups, there will be 6 or 8 layers of fiber. Do we understand next week's lab? Yes. Let's go. And do you have any questions? Okay. I guess that's it. How's it? How are you?